Good afternoon again. So today I'm going to give 2 consecutive lectures, okay? And so they aren't going to be at all they're much more clinically oriented. There's one thing where I want to develop theory in the second talk about the flow measurements, but that's the only thing that's sort of like the first day. So my plan then is to first spend the second lecture basically talking about imaging in the context of breast cancer only. And in particular, I'll say a little bit more now about tissue physiology and clinical potential in this context. And then I want to tell you sort of about experiments from my lab, although it's reflective really of a lot of activity in the community. So it's not, but it's just easier for me to talk about what we've done. And then, so for example, I'll talk about sort of what I would say traditional diffuse optical tomography of breast to distinguish malignant tissues from normal tissues and malignant tissues from benign tissues. Then I want to tell you sort of some essentially kind of computer-aided diagnosis approach. It's kind of like a machine learning approach, if you want to use that word, to do this better. Then I'll switch, and I want to talk about another kind of problem having to do with breast cancer, namely response to therapy, chemotherapy, and I'll show you some results that we've had with that. And then finally, I want to touch base back again on the contrast agents, okay? Because I told you about fluorescence at the end, and I didn't tell you that for no reason, okay? Okay, so just again, to remind you, I talked about a little bit about what we can measure. The biggest thing that we measure is absorption variations. And so in principle, that gives us access to everything in the tissue that has an absorption spectrum in the near infrared that's significant. And that includes water and lipid, but the main workhorse is oxy and deoxyhemoglobin, from which we can derive total hemoglobin concentration, which is the sum of them, and blood oxygen saturation, which was the ratio of the oxygenated hemoglobin to the total hemoglobin. We can also look at scattering. I won't be talking about that today, though. The other thing, as I mentioned, that I'll say something about towards the end is you basically measuring a fluorescence, not of an endogenous contrast, but of exogenous contrast. And I'll show you some measurements about that. Okay, so these variables, which I'll come back to later, are useful for lots of things in the clinic, okay? I've listed a bunch of them here. And again, today, in this lecture 2, I'm going to just talk about cancer, okay? And so let's do that, okay? So the first thing then is just conventional diffuse optical tomography of the breast. Why would you want to do that? Okay, well, there's definitely some niches that diffuse optics can have in this context. As you know, it's non-ionizing, non-invasive technique that uses non-ionizing radiation. In principle, it's portable and rapid and inexpensive. You know, our instrument is for the tomography is actually not that portable, but it's pretty fast and it's comparatively inexpensive compared to like an MRI or something. And there's complementary contrast. We have lots of access to hemodynamics. That's the biggest thing. But also we can learn about water and lipid, and I'll show you why that might be interesting as well. And then there's, of course, molecular targeting agents. One thing that's accessible to the diffuse optical techniques that's harder with X-ray is women with radiographically dense breasts. Okay, so generally that's almost all younger women, but also some older women as well. And so there's really an opportunity to look with light there regularly. And similarly, if you have patients with a genetic predisposition to getting breast cancer, then you might want to be studying them often, okay? And so, again, since it's non-ionizing radiation, it's not a big deal to do that often, okay? So these are things that I think are important. And then there's a fair amount of work including from our group, but where basically you can combine diffuse optics with other techniques like X-ray or like MRI, or like ultrasound, okay? And that actually can be used to improve the sensitivity and specificity of the techniques. And finally, and I'll emphasize this with the chemotherapy, with the optical technique, you have the opportunity really at the bedside, or really very often, to monitor a patient that's undergoing therapy, and then you can look at how that therapy is working. So at Penn, we built this Regino Che basically spent a lot of time and put together a nice optical tomography system. And in this particular case, right, it's basically the table is a sort of a needle biopsy table, okay? And you can sort of see all the fibers over here. And what basically the way this works was it's a soft compression device where a woman would lie down, her breasts would hang in a box. Often we were filling that with intralipid, okay? And then we have a source plate with many, many sources and even some detecting fibers on this plate. We also had a CCD camera, which we gated at high frequency, so we could measure, in general, this has gone through a lot of iterations, actually, but so generally we have a lot of, a fair number of wavelengths, 6 wavelengths, of 50 sources or so, a whole bunch of measurements in transmission, and then some measurements in remission. And it's a soft compression device. We get about 1 million measurements in about 10 minutes, okay? And then we basically take those measurements, remember those are on the surface of the tissue, we do the tomography, we do the inversion, and basically we construct a 3-dimensional image. Now usually, even though it's a 3-dimensional image, the way that it's presented to the radiologist and the way I'll present it to you generally is in slices. So they could be slices, for example, 1 centimeter apart from the source plane to the detector plane. And so, they might have a tumor, for example, somewhere in the middle or close to one of the plates. Here's again a picture of this detection plane with the detector as the source plane, okay? And so basically, this imaging, this is basically one of our 3-dimensional tomography images of a cancerous lesion in the breast. Basically, we can get them, okay? And these are images actually, because we're doing these measurements at multiple wavelengths, which are sensitive not just to like an X-ray, right? You're measuring just X-ray contrast. Ultrasound, it's sort of the impedance of the sound wave. Here we can measure lots of different physiological parameters. We can look at hemoglobin concentration, oxygen saturation, scattering. We can construct variables that combine them that have more sensitivity. And so, for example, here is now doing these 6 slices. So going from the source plane to the detector plane, you can see this is an image of total hemoglobin concentration. This is an image of blood oxygen saturation. This is an image of scattering. I'm going to show you an optical index, which is sort of related to the product of this thing times this thing divided by this thing, right? And you can have reason to believe that that might have more sensitivity than any of the individual variables. And you can see in this case, you can see a tumor is sort of showing up here, both in the absorption and in the scattering, but not in the saturation. Here's another image. This is now just the slice in the biggest, where the tumor is the biggest, in the middle of the breast. This is an invasive ductal carcinoma. These are MRIs of it. And you can see there's a large contrast. When I put an R, that means the relative change of total hemoglobin concentration, the tumorous lesion compared to the background, okay? And so you can see that, again, we have contrast in the hemoglobin concentration, the total hemoglobin concentration. In this case, we didn't have much contrast in the oxygen saturation. We had contrast in this scattering. We can construct that optical index to make that a little sharper. So that's good. We can distinguish malignant lesions from normal tissues pretty well. What we really want to be able to do is to distinguish malignant lesions from benign lesions. So here's a case where a patient had a cyst and an invasive ductal carcinoma, and you can sort of see both. This is basically where the cyst is. It has a low amount of of hemoglobin. It's of course has a low saturation. We can see the invasive ductal carcinoma best in this scattering image in this case, and so you can see the both of them. Anyway, so we basically set this up and looked at a bunch of patients. Here's results, and I should say again, there's other folks, especially Brian Pogue at Dartmouth, did a lot of work on this problem, and basically came to similar conclusions, that in fact you can have, just based on endogenous contrast, okay, so the natural contrast of your tissue compared to your, your lesion regions compared to your normal tissues, there's natural contrast in these blood variables, in part because the metabolism is different and in part because the vasculature is different. And so basically, this is a plot I'm showing of our malignant patients and malignant and benign lesions. I think this is about 50 patients. And one is sort of, we normalized everything, right? So we're comparing always to the average value in the breast. And so you can see that there's a contrast. We can distinguish malignant from normal, but also we can, in fact, if you look at it, we can have a reasonably good separation between malignant and benign tissues, especially when we start to look at this optical index. And so, at this point, we were pretty happy about this. But, and so we were encouraged, but, now I want to think about, can we do better? And what I want to tell you about next is essentially the, the answer to that thing, and that is that, yes, we can. And so we did, what I'm going to tell you about is sort of a computer-aided diagnosis analysis, which takes advantage of all of the data we have, and I'll tell you what I mean by that, to categorize, if you like, assign a probability of malignancy to each volume element in these tissues. And so, just to sort of put that into perspective, whenever in our community, when people sort of say, look for contrast between a cancerous lesion and a normal tissue, or cancerous and malignant and benign lesions, basically what they do is they make a measurement of the average properties of the lesion region and the average properties of the normal region, and they just take the ratio. That's all we've been doing, that's all Brian was doing. But actually, if you look at all that, we have many, many volume elements of normal tissue, for example. We have many, many volume elements even for the cancerous tissues. And so this is, if you like, so I just focused here just on relative total hemoglobin concentration, which is, again, this is the total hemoglobin concentration divided by the average value of the healthy tissue. And the main point I just want to make is, this is a histogram of the different voxels in one person, okay? And this is a pretty broad distribution, okay? So there's a pretty broad distribution of normal tissue, even in the same person, okay? When you go from person to person, also, there's a greater heterogeneity. And so what we're relying on is taking sort of an average value of the tumor tissue, which also has a distribution, and hoping that it's different than this normal tissue, okay? And that's not very efficient. It's not really using the data very well. And so, again, just to reiterate, we have a lot of data in our images. That three-dimensional image that you saw has lots of volume elements. And in each volume element, we have several different physiological properties. So can we use it all? So the answer is we can, and I'm going to show you what we do. I'm going to use a 2D illustration just to make it simpler. Okay, but remember, we're going to analyze data from that same study in 3D. Okay? And so just imagine then, and I have a 2D scan, this is a breast. This is the nipple. There's a tumor here in this region here. There's sort of a region that's around the tumor, which we don't know what it is necessarily. And then there's a region that we can sort of pretty well decide is normal. Okay? And so what I'm going to do, but anyway, the main point, first of all, is that there's lots of data points here. And before, basically, I'm just using one data point to represent the normal tissue and one data point to represent the average value of the tumor, okay? So what I'm going to do is I want to use the normal tissue data in another way. I'm going to basically figure out its average for sure, but I'm going to get the whole distribution at least, so I can get a standard deviation as well of that average. And then, again, for each point in this, throughout the whole breast, actually, I'm going to redefine the variables. Okay, I'm going to introduce again this. You'll see when you look at this, you'll say, well, this is sort of standard statistics, and it is really kind of standard statistics, but it wasn't really being used. okay? And I think it has a lot of potential. So I want to tell you about this new variable, the z-score variable. So before I told you that we're measuring, say, hemoglobin concentration or oxyhemoglobin concentration, say. That's what the xj represents here. So the z-score variable is just like what you have in regular statistics, except that you take the log of it. So all statisticians usually take the log of their variables to reduce the wings, to bring the wings in. But basically, you can see that I'm comparing sort of the value at a given volume element to an average value of the normal tissues divided by the standard deviation of the normal tissues, okay? So just to reiterate this, right? So there's normal tissue. I know that it's normal. I make measurements and I determine, say, oxyhemoglobin in each of those. And I figure out what's the average value of the log of it. But I also look at the standard deviation of that distribution and I divide by that standard deviation. So if it's a really wide standard deviation, right, then you're going to have a pretty big contrast, a pretty big difference between tumor and normal. But basically what this does is it puts all variables on the same footing in terms of the standard of the fluctuations of the signals. And then, this other one might be, for example, measured in the tumor, okay? And I can do, I can do it for each volume element in the tumor, or I could take the average of all the volume elements in the tumor, and that's still an average of the z-score variable, okay? So that's all we did. But it really, first of all, I just want to point out, it really had a hugely positive effect to do this, okay? So like this is basically the oxygen saturation measured in a whole bunch of patients. I think this is anyway, so mainly this is, I think this is a different subset of a different group of patients, but basically you get the idea, I hope, that from patient to patient, which are the different colors, it's different, okay? But even within a patient, if you look at the distribution, it's pretty broadly distributed. But so there's intersubject heterogeneity, there's intra-subject heterogeneity, and then it might look like this for SDO2, but it might look like something different for scattering or for total hemoglobin concentration. So when I take this, when I do this average and I determine these z-score variables, then all of these curves are contracted onto this nice, fairly Gaussian kind of distribution centered on 0, okay, with a well-defined width, okay? So we basically not only got rid of all these different intersubject heterogeneities, but we made it more of a normal distribution, so the statistics are going to work better. And we've also basically made it much easier to compare different features than before. Okay? So with this z-score variable then, what do we do with it? Okay? Well, what we want to do, the goal of this thing I'm going to first tell you, is just to get a better classification between malignant and non-malignant tissue. Okay? So for, if you like, for each patient and for each volume element in principle, right, we have a z-score variable for these different variables that we had before. So we can have one for, again, deoxyhemoglobin, oxyhemoglobin, water, lipid, scattering, other things. And then I'm going to define a weight vector, which is basically, essentially a weighting of how important these different parameters are. And that could be positive or negative. Okay, it could be correlated or anti-correlated. And I'm going to define a malignancy parameter, m, which is basically the dot product, if you like, of this vector with this vector, okay? And then all we do is we sort of demand, because again, we know from our data, we have a training set, if you like, where we know which tissues are malignant and we know which tissues are normal, okay? And we can define kind of sort of a standard kind of S-curve probability of malignancy in terms of this variable m. So I define it here, 1 over 1 plus e to the minus m. And so with this language, the probability of malignancy is when it's 1, it's malignant. When it's 0, it's not malignant. But the higher it is, the more likely it is to be malignant, okay? And so essentially I take all of that data that I had, all the different volume elements, all the different parameters, and I train it to figure out the beta, the best optimum beta vector, okay? And then, just to make a long story short, what David Bush did, actually, is he sort of found out, the best combination of these three variables, for example, that predicted probability of malignancy for our sample set of 50 patients, okay? And he could even figure out an AUC curve, if you like, by using a leave one out protocol, right? Where you train it on 49 of the 50, and then you test it on the 50th. Then you do a different 49, and you train it, and you test it on the leftover one. So that's called a leave one out protocol. And that's what you can do if you didn't have like hundreds of patients. Okay, that's a standard trick. And it really, once you have this, you can very easily get an image, and you can make a mask to say this region is very likely to be tumorous, and it's much less sensitive to operator usage. And then again, you can have this situation where we have a much better prediction of what tissue is malignant compared to benign. So anyway, that hopefully then introduces you to what I would call the standard diffuse optical tomography of breast. And what I wanted, and also this computer-aided diagnosis and the Z variable. And now what I want to do is to say a little bit about another related problem, which is not necessarily looking to see whether tissue is malignant or benign or normal, but looking at only malignant tissue and asking whether it's going to respond to chemotherapy or not, okay? And so this is a project, again, led by Jeff Cochran. And what we have a project, basically this is a group of patients that we've been looking at with a number of other groups actually around the US, that basically studying neoadjuvant chemotherapy. I'll say something about what that is. And basically looking to see, can these optical biomarkers at an early stage or at a middle stage predict whether this therapy will work or not, okay? So let me just remind you a little bit about that, okay? So neoadjuvant chemotherapy, right? This is usually used for women that have a large tumors, okay? And so what you do is before you go to surgery, you get a chemotherapy treatment, okay? And that idea is to reduce the tumor size and, in fact, kill it as well as you can before you go in there and do surgery. And so you can actually, in these studies, define whether there's a complete pathological response to the neoadjuvant therapy or not. So it's kind of a binary thing, just like malignant or not malignant, okay? And so by way of background, we are part of the people in red here are from Penn, but this is a big multi-center trial with 5 different groups led by Bruce Tromberg, who was at UC Irvine at that time, and has a group from Dartmouth, has a group from MGH, San Francisco, and I think in the MD Anderson Cancer Center in Houston. And basically, I'm going to show you the results of this. First, I'll show you the results of the main trial. Then I'll show you what happens when we use these z-score variables, okay? So in the main trial, we had a very modest goal, and that is to make a measurement at the middle. We're going to do an imaging measurement, but basically make a measurement of optical properties at the time point in the middle of the treatment and look to see whether that was predictive or not of response, okay? So this measurement actually used the device which you could scan. So it's not like the tomographic device that I showed you in the first part, which is really a standalone instrument. This is something that it's a handheld device that you can scan over the breast, and so it's not really giving 3-dimensional images in the same way, right? It's basically giving more of a topographic kind of image. But there's a lot of data still, and you can know where the tumor is and know where it's not using these, from palpation even, but also from these scans. And this device is basically a device, as I told you about yesterday. Basically, it's a device where there's a source and detector, and it's interrogating some distance underneath the probes, typically a few, a couple centimeters, or between 1 and 2 centimeters. And then it combines measurements at 6 wavelengths that are modulated with broadband spectroscopy. And at the end of the day, you can actually determine, again, the absorption and scattering properties, and from those, as a function of wavelength, you can get the oxy and deoxyhemoglobin, water and lipid, okay? And so what we did is we did this measurement at these 5 different places with the same instrument, okay? And essentially, we would measure it, so this is sort of a timeline. We'd make a measurement sort of before you're getting therapy of the breast, and basically after the treatment starts, at an early time, within like 10 days, a week to 10 days. We measure it at a mid-therapy point, and then we, after the therapy was over, we make a measurement, before surgery though, okay? And again, for these accurate trials, you have to actually have a very well-defined goal before you do the measurements, and so we sort of had reason to believe that we thought this would be a good one, and actually now I think it wasn't the best one, but basically we looked at this tissue optical index, which was related to deoxyhemoglobin concentration, water concentration divided by lipid concentration at the midpoint. We looked at the value of that in the tumor region compared to the normal tissue, that ratio different for responders compared to non-responders to this chemotherapy. And so here's sort of a summary of the result. This is for all of the subjects. This is non-responders and responders. And if you look at this, you can see that we had a marginally significant effect, okay, at the midpoint in distinguishing between responders and non-responders. If we actually made one cut, and we just took people with breast tumors that had a higher than average oxygen saturation, then we got a better difference. But to me, actually, this is a good thing that we were able to do this and do this across these different trial groups, but it was a kind of a disappointing result. And so what we thought about in my group then was, can we do this z-score normalization, the data, and do better, okay? And in particular, it may be that there are different variables, like that was just the ratio of that tissue optical index from the lesion to the normal tissue. But can you do better with other variables? And especially, can you predict whether it's going to respond at an earlier time point? Because if you can predict whether it's going to respond at an earlier time point, then you can actually you could change the treatment. Some drugs the tumor's not responding to, you could change it, okay? And so we did. Now, you've seen this already, okay? Because I organized my talk so it would look the same, okay? But basically, the only difference is that instead of looking for a malignancy parameter, we're just looking for a responder or not responder, okay? But we make the same measurements of oxy and deoxyhemoglobin and water and lipid. We construct this, I would say, responsivity parameter, which is a dot product of these two vectors. And then we know from the data whether somebody responded or not, okay? And we can use that as a training set, okay, to come up with a probability of response which looks like this, and which has sort of the optimized data, okay? And again, just to remind you, what we do for all of these kinds of studies where you only have a small number of subjects, because again, ideally you have one subject that you train, and one group that you could train on that could be like 300 subjects, and then test it on 100 subjects. But we only have 35 or 33 in this case. And so what we do in these training things is you train it on everything but one, and then test it on one. But then you switch it around. You do that for all the different ones, and you can come up with the best estimate of this beta vector. And what we found was that the early time oxygen saturation had the best probability of predicting whether it would be a responder or not a responder. And it was really a very good, if you remember, if you looked at that box plot before, they were practically overlapping. This was dramatically better, okay? And so, this is exciting for us. It's exciting for everybody in that collaboration. There are other things you could look at too. So this is a measurement saying basically, it's just saying from the same set of measurements, if I looked at that early time point of the oxygen saturation, if the tumor, we can easily distinguish the difference, okay? And it's just comparing, again, the value, you're comparing, essentially, in the z-score, it's already built in the normalization, right? It's already built in the normalization to the average value of the normal tissue and also to the standard deviation of the normal tissue. We also found out that if you just looked at the baseline z-score of the oxygen saturation before you started the chemotherapy treatment, it wasn't as good as if you looked at the early time point. So you could see how the tumor is remodeling compared to the other tissue when it's responding compared to not responding. But it still was pretty good. It was still pretty helpful. Okay? So in this study so far, then, what we've seen is that this z-score normalization, it's improving prediction power. And it's in this case, for the chemotherapy response, you can get a pretty robust prediction within 10 days based on really, if you just took the very best one, and it was clearly the best one, just the oxygen saturation at the early time. And but of course, there's lots more to understand. And there's really a lot to understand about what's the physiology that's driving this. And that's something that we've been working on. Okay? And I should say, in going around to see the posters this morning, there's all sorts of imaging that's done in, looking at microscope images, really, in most of the cases. And really, they're not, I think that there's a lot of potential just to apply the z-score idea there. And it's just a standard statistical trick. It's not that hard. Okay, so then the other thing I wanted to just bring your attention to was going back to fluorescence, okay? So everything I've been telling you about is really non-invasive. It's truly non-invasive. We're not injecting anything. We're just relying on a normal contrast. But still, if you look at it, it wasn't really that big a contrast, right? I mean, it was about 1.2 to 1 or 1.3 to 1 at the best, okay? So there's this hope. And again, I'm sure Gongzang is going to talk about this next week. But basically, all of us have a hope that that exogenous contrast agents can be developed that target tumors much more than normal tissue. And fluorescence, right? You can measure fluorescence all the way single photon counting. And if you really were confident that you had no signal in your tumor compared to your background, then you could detect tumors really, really well, okay? And so that's a challenge for the people developing the probes. But so we're sort of on the side of developing the optics to take advantage of those probes. And so what we did is we did one thing which I feel is exciting, actually, still, to do diffuse optical tomography. Again, it was in the same apparatus that I showed you earlier that Regina put together for measuring the endogenous properties. But we looked at 5 patients where we injected a contrast agent, okay? So this is, so this is work by Regina again, but also with Alper Korlu. And basically, again, our motivation is that we thought maybe fluorescent signals can provide a better detection sensitivity and specificity compared to the endogenous absorption changes, which are small. And then, if we can do these kinds of tomography for fluorescence, in principle, there's all sorts of other kinds of information that would be accessible to us if you can get these fluorophores into human tissues, namely tissue PO2, calcium. There are all sorts of things, pH, that these fluorophore reporters can detect, in principle. And so what we did then is we applied this to using the one drug that's FDA approved in the US, indocyanine green, okay? So this is a blood pool agent generally, and so let me just show it first, right? So basically, here's again, I showed it yesterday in experiments. We did it using experiments in those aquariums, but here again, just to remind you, there's an excitation region and an emission region, and we are going to excite using some diffusive waves that are, say, 780 nanometers, and we'll detect it way over here at, say, 830 nanometers. And here's the molecule indocyanine green. And what we want to do is to look at the uptake of that. But let me just go back. And again, I'm not going to tell, I just want to tell you that we can do this, okay? But the problem is more complicated because remember, the fluorescence signal depends on a lot of things. It depends on you having fluorophore or ICG in this case, at the tumor site. But it also depends on you're getting light to that tumor site, okay? So you have to actually solve two problems. This is the problem for the excitation wave that you're sending into the medium from your laser. And so you have to actually, and there could be heterogeneities in the breast, right? So you have to first figure out what is the distribution, or an optimal distribution of this photon fluence rate at the excitation wavelength in the breast. And then you use that as a source, okay, in the source term that's in this thing here, to figure out what's the fluence rate at the emission wavelength that's going to be detected on the surface. And so we have to do this together. So it's non-trivial, but doable. And so what we did then is we inject a bolus of this ICG into the patient. Before we inject the bolus, though, we do all of our tomography for the endogenous. And so we figure out what the phi is at the excitation wavelength. And then here you can see this is just looking at the peak intensity of the fluorescence at one position in the detection side. And you can see it goes up, and then it comes down. And then when it comes down to a certain, there's a certain amount of freedom here about what's the best time to choose. But so we let it fall down a little bit, maybe about by a factor of 2. And then for the next 10 minutes or so, we did a full fluorescence tomography. So we detected, in that case, we scanned through all of our sources at the right wavelength, and we detected the fluorescence at 830 on all of our detectors, okay? And then we inverted that data, okay? And I just want to show you one result, which is shown here. So this is one patient. Here's the tumor region. And this is the plot of endogenous contrast at hemoglobin concentration, blood oxygen saturation, scattering. And if you look at this, if you just look at this line here, that corresponds to this curve here. There's a little contrast. And I would say this is good. These detected that there are tumors there. But then it's not really very big, okay? And so here's what we saw when we did the inversion for the ICG, okay? And it's like enormously bigger. And so averaged over 5 patients, we typically are getting 4-to-1 contrast looking at the fluorescence compared to the endogenous contrast, which is closer to like 1.5 to 1 or something, and that's a good day, okay? So I want to leave it at this point because I think that there's a lot of potential for using these exogenous contrast agents to the degree that we can get them to work, okay? And to get them through the FDA, for example. But there's really, this is probably one of the least targeting agents of all, right? And it works that much better anyway. Okay, so actually that's the end of my lecture 1. We can, any questions about that? And then we can stand up and stretch for a second. Yeah, go ahead. There's someone there. Yeah.
Hello, my name is Ronald. Thank you for the lecture. My question was more about the logistic regression model. Why did you pick logistic regression against other statistical models or any machine learning algorithms? And my second question is about the leave one out. Did you do it by patient, by sample, and why? Thank you.
Okay, so actually, when people talk about machine learning, I consider that to be linear algebra. Okay, basically, you're finding some hyperplane in space which is best separating 2 sets of variables. There might be 94-dimensional variables or something, but so there's different languages that you can use for linear or nonlinear machine learning approaches that to me are similar to the regression. So I'm sure there are a lot of other ways that we could do it. We just did it in the most standard way, okay? And actually, I'm doing work in other areas where we're doing the same thing, but they call it machine learning. Everybody's super excited about it, okay? And so, so first of all, there's more than one way to do it. This is one standard way, okay? That form of that function is a standard kind of a form, but it's linear. So then the question about the leave one out protocol. Okay, so that's the basically, ideally, like I said, what you want to do is to have a big patient population and then make a training set to be a fraction of it and test it on the other fraction. That's the way to do it if you can. But if you have a small amount of patients, then this is a standard statistical trick which is well established and reasonably good. And there are ways to actually look at how good it is, okay, which I didn't go into. And so it's the way essentially you can evaluate the area under curve, AUC curves, using a small data set. So it is a standard trick. It's not perfect. There's ways to see whether it's not perfect. You know, these were pretty good. Okay. There's somebody there.
Hi.
Sorry.
Hi. I also have a question about your logistic regression. So you've essentially done your linear weighting, your offset, and then a sigmoid. So that's one layer of a neural network. Have you tried stacking that same trick on top of each other 2 to 3 times?
Oh, it's a good thing to do. We were just very simple-minded. You had a question?
So what's the resolution you need for the STO2 in the endogenous case?
It's a good question. So basically, so first of all, the answer to that question is it's about 1/2 centimeter, okay? But basically,
I'm sorry.
The resolution in the diffuse optical, is that what your question was?
It's about
Spatial resolution?
5% of what's the resolution in percentage of STO2?
Oh, okay. So, you know, for monitoring, if you're looking for changes, a percent, even a percent could do.
A few percent?
Yeah, yeah.
Okay, thank you.
But I thought you were asking about spatial, but then I won't answer the question. Okay.
Thank you, Prof.
Yeah.
Prof, please, I want to know, did you put into consideration the optical biomarkers for the aggressive type of breast cancer, like the triple-negative breast cancer in the diagnosis?
Okay, I didn't understand your something about the contrast agents.
Yeah, my question is, did you, in the optical biomarkers, did you put into consideration the triple-negative type of breast cancer for the response in the neoadjuvant chemotherapy?
Oh, yeah. So again, we did keep track of all that. But it's still a pretty small number. So we couldn't make any major statistical conclusions about that. It's a good question, though. We need a bigger sample for that.
I have a question. Yeah. So if you have a patient that had already been under treatment of radiation therapy, and then you want to try to find a recidive, a possible recidive lesion, do you think there is enough resolution? If a patient had been already treated by radiation therapy,
okay,
and then we are tracking to see if there is any potential or possible recidive lesion.
Oh, residual.
Yeah, yeah.
Yeah. So that's, I mean, it depends how big it is and how big the contrast is. So I don't have a good answer to that question. We never did that. But
because it changed a lot,
yeah.
All the vascularization.
Yeah, sure. I guess I would feel hopeful about that. But I would still feel more hopeful with a contrast agent. Because really, if you can get if you can get a contrast agent that really likes to go 10 times more, even 5 times more to the tumor than the background, then it can be very small and you can detect
lesions.
it.
Yeah, sure.
So we can be we can detect things. To spatially resolve them is harder, okay? But to detect that it's there, I think is easier. Yeah.
I have a question also,
oh,
Professor.
Yeah.
Go first. Yeah.
Yeah, sure. I have already seen some other groups trying to do wearable probes for TOSI. Is this a great challenge? Is this very difficult to do? Wearable probes?
Variable probes.
Wearable, yeah.
Oh, wearable probes.
Yeah.
I think that's possible. I don't actually see that big an advantage of it for cancer. I do think it's good for brain. Maybe that, when I talk about brain next, you'll see what I'm saying. But for cancer, you just want to make the measurement, make a good measurement, And as long as you can sort of have a good fiducials about where you're, especially if you're following something over time, if it's day to day or week to week. And so just as long as you can get it roughly in the same place, that's the critical thing. You don't have to be wearing it all the time. The advantage of wearing it all the time, though, I suppose, is that it would be, if it was really staying in the same place, that could be good.
Thanks.
Yeah. Yeah.
So going back to the spatial resolution,
Yeah.
How deep can you go?
Yeah.
And does having a contrast agent change how deep can you detect?
Yeah, good. So anyway, just for concreteness, that we were going through breast, in that breast is actually one of the easiest tissues to go through, to be honest. But we are going through as much as 10 centimeters, okay? So, and then, essentially you can look throughout the medium. If you do an experiment like in the brain, where you have a source detector like this, then pretty much the depth you can probe is set by the separation. And it's about half to a third of the separation. So, so I don't think that having a fluorophore improves your spatial resolution, but it can improve your sensitivity. Okay, so now I just want everybody to stand up and stretch for a minute before I go to my second one. So, another question, good. But you can stand up. Okay.
Hello, thank you for your nice presentation. Excuse my ignorance because I've got no idea of what is it. I would like to know, you only use the contrast agent if you have, let's say, any targeted therapy that mainly promotes accumulation only in the tumor tissue. Or will it enable to enhance your analysis? Will it be, okay, will it improve your analysis or?
No, yeah, so if you can get more, okay, so this is like, ICG is like a blood pool agent, something like that. I mean, if you can get something that targets like something in the cancer, a molecular target. Again, Gang Zhang is an expert about this, right? He'll be talking next week. So I'd say that there's lots of things that have been done in animals that seem promising. I will tell you that when I first started in this field, which is a long time ago because I'm old, basically, essentially, people were talking about the same thing. They would get these agents to through the FDA. There has been a lot of progress, but not that much more has gotten through the FDA. Because in a way, you have to prove that it's going to be helpful to get it through, right? So you have to, there's a lot of things that had to be done, but I think we're in a good position to look at it. And I feel optimistic, to be honest.